Deterministic preparation of single neutral atoms in optical traps is a subject of interest due to their potential use in quantum logic devices. For more than a decade, different avenues have been pursued to achieve this goal, exploring different trap geometries and parameters suitable for the various purposes for having the trapped single atoms. In this paper, we will demonstrate one of the methods that can be used to efficiently prepare single atoms, and this is done in a tight optical microtrap in the collisional blockade regime. Loading single atoms in tight optical microtraps are important for some applications. For example, these microtraps are used to interface optically trapped individual atoms with microfabricated solid-state structures to create hybrid devices. Tight traps are also used for the manipulation of single atoms, such as the Raman sideband cooling of single atoms to its motional ground state. The results of our work may also be useful for some applications that require direct loading of individual atoms into arrays of tight traps, such as optical lattices. However, when loading single atom into a tight microtrap from a reservoir of atoms provided by a magneto-optical trap, or MOT, collisional blockade takes effect, where the volume of the microtrap is so small such that the light-assisted collisions induced by the MOT lasers often cause rapid two-atom loss as soon as a second atom enters the trap. This prohibits the microtrap from being occupied by more than one atom at a given time, and the single atom loading efficiency in the collisional blockade regime has been previously reported to be around 50%. The combination of laser cooling and light-assisted collisions induced by blue deuterium light can lead to a two-atom repulsive collisional process, where only one of the two colliding atoms is lost from the trap. The energy released by the atoms upon collisions are limited by the detuning of the blue deuterium light from atomic resonances. The detuning can be chosen in a fashion such that the pair of atoms after the collision has a total energy that gives finite probabilities that the collisions will lead to one or none of the atoms escaping. If none are lost, then the laser cooling removes the energy released in the collision, and this returns the atoms to the starting condition, and the process repeats until one of the two atoms is lost. The question that we have here is that if we want to load single atom into a tight microtrap where collisional blockade takes effect, is it possible to improve the 50% single atom loading efficiency by applying a blue deuterium light to implement the 2-to-1 loss during loading? The idea is that if the timescale of 2-to-1 loss can be made faster than the timescale of 2-to-0 loss induced by the MOT lasers, then it is more likely that only one of the two colliding atoms will be lost from the trap, instead of two atoms are lost altogether. When this is implemented, we find that the single atom loading efficiency in collisional blockade regime to be about 80%. We also describe the loading dynamics and investigate the dependence of the loading efficiency on the trap potentials and lasers parameters.